pleasure to have Leandro Martinez from the Institute of Chemistry, and he's going to talk about concurrent value optimization methods in molecular modeling. Thank you very much.
So, I also work with molecular dynamic simulations as Jim and Munir, and this is actually my specialty, but since the audience was a little bit more diversified, I decided to talk about some project that we have that involves molecular modeling as well, and also some techniques that some ways to see the molecular modeling problems that may be of broader applicability. So maybe this is interesting for someone that's not actually working in molecular modeling. So I'll be talking about this type of problem that we call concurrent value optimization methods, concurrent value optimization problems, and the methods that we use to solve them, and the applications we have developed in the context of molecular modeling and the problems we are working with. Concurrent value optimization is a problem that is defined in the following way. Suppose that we have multiple functions that assume different values in the same domain. So we have several functions that are acting in the same domain, and what we want in the concurrent value optimization problem is to optimize the maximal value assumed by all these functions, or minimize the minimum value assumed by all these functions. And so, for example, here we have all these three functions. These three functions are overlapped here in the same domain. The objective function we are trying to maximize in this case assumes the maximum value of all these functions that are concurring in the same domain. So the goal of the concurrent value optimization problem is to maximize the maximum value of a set of functions that are defined in the same space. The interesting thing about the interesting thing about thinking of problems in this way is that the objective function is clearly non-smooth. When we have crossings, for example, of two functions in the same point, these functions, the orange functions are concurring, and we have here a crossing between two of the orange functions. The objective function that we are trying to maximize, which is the maximum of all the functions, is non-smooth in the points of the crossing, in spite of the fact that the functions, the orange functions themselves, are smooth. However, this kind of non-smoothness of the objective function is a benign kind of non-smoothness. What does that mean? That means that suppose that we are in this point of the domain, and we are exactly in the point of where two orange functions are crossing with each other, and we want to move in our optimization procedure in such a way to obtain a direction that maximizes the value of the function. So in spite of we in principle should not have derivative information in this point because the objective function is non-smooth, but nevertheless we can choose any of the concurrent derivatives or the concurrent gradients of the competing functions at this point, and any of these concurrent gradients will give us a direction of increase of the objective function. Therefore, while the objective function is non-smooth, we can apply every kind of smooth optimization method to the solution of this non-smooth optimization problem. And there is a lot of smooth optimization methods that are very well established with convergence theories and so on. So we can use a lot of powerful computational methodologies, powerful optimization methods to maximize or to minimize a function which is non-smooth in principle, but that can be treated by smooth methods. So how this behaves in practice? So when we want to maximize, when we want to optimize a function that can be treated as a concurrent value function, we have two steps. First, suppose that we have that we are in this point of the domain. So we need to recognize which is the concurrent function that is assuming the actual value of the objective function at that point of the domain. So we need to recognize at this point of the domain which is the function that is concurring with the other functions that assumes the maximum value. So once we identify which is the function that assumes the maximum value at this point of the domain, we can apply a smooth optimization algorithm, conjugate gradients or anything else, to maximize the value of this concurrent function. So applying a smooth optimization algorithm will lead us to increase the value of the function we are maximizing, of the concurrent function we are maximizing, and for example go to this point of the domain. Now we are in a new point of the domain, and we have to know how to, in this new point of the domain, obtain again which is the concurrent function that is maximizing, which is the maximizer of, which is the concurrent function that assumes the maximum value at this new point of the domain. And if we know how to do that, we can now move from this concurrent function to the other concurrent function and apply again the smooth optimization algorithm to obtain the maximizer of the actual objective function. So if we are trying to maximize this, if we know how to apply these two steps in some given problem, if we know how to, given a point of the domain, recognize which is the concurrent function that maximizes the function value, that defines the function value, which is the maximum of all concurrent functions at that point, and we know how to apply a smooth optimization procedure to this concurrent function, we have a well-defined method to maximize a function which is non-smooth in principle, but can be optimized with this iterative procedure. So one of the problems is how can we recognize which is the function which is the function that's concurring at each point of the domain that assumes the maximum value. So therefore we have to recognize which is the function that actually is taking us to the objective function that we're trying to maximize. And this is problem dependent. Of course, there are some problems that can be well defined in terms of concurrent value optimization problems, that are other problems that not. But the thing is that many interesting molecular modeling problems can be treated within the concurrent value optimization framework. I have changed the name for it. So the three examples of problems that can be treated within this framework that I'm going to mention here are: first, general protein structural alignments and the analysis of fluctuations in molecular dynamics trajectories. This is a problem that can be interpreted as a concurrent value optimization problem, and the techniques are quite nice. Another problem that I will be speaking a little bit are linear interaction energy models for the determination of free energies using crude models. And finally, the thing we are working now is structure determination using partially wrong or ambiguous distance restraint data. All these problems, which are molecular modeling problems, can be interpreted as concurrent value optimization problems, and this leads to the definition of well-defined algorithms for the optimization of these functions. First, we are going to talk about the general protein alignment problem. So the protein alignment problem depends on two steps. First, we need to find out which are the atoms of one structure that correspond to the atoms of this second structure. So for example, here I have defined that this is the correspondence between the atoms of the two structures. And if I know, I have defined which is the correspondence between the atoms which is the correspondence between the atoms of the two structures, I have now to move one of the structures in order to improve the superposition of these atoms. So there I have moved, I move one of the structures to obtain the best movement of one of the structures that superimpose the corresponding atoms. Now I have a new relative orientation of the structures in space, and this defines a new, I can use this new relative orientation of the structures in space to define a new correspondence between atoms. And with this new correspondence between atoms, I can now move again this one of the structures in order to obtain the best movement that superimposes the atoms of the two structures involved. So a structural alignment problem can be separated in two phases. One is to obtain the correspondence between atoms. One is to actually perform the structural alignment, the structural movements of one of the proteins that lead to the best superimposition, to the best overlap of the corresponding atoms. So that means that we can think of the structural alignment problem as a concurrent value optimization problem. In what sense? For example, we can have many different correspondences between atoms. For example, here atom 1 corresponds to atom 1, but here atom 1 corresponds to atom 2, and so on. There are many combinatorial ways to correspond atoms between the two structures. For each given correspondence, there is a function, a well-defined smooth function, that can be used to compute what is the quality of the overlap of the two structures for that given correspondence between atoms. So for each of these correspondence, there is a different function, which is the score of our structural alignment as a function of the movements, rigid body or not, of the rotations and translations of one of the structures relative to the other. So what we want to obtain is, given all these concurrent functions, we want to obtain which is the maximizer of all of these functions. We want to obtain which is the correspondence and the movements that maximize the quality of the overlap between the two structures. So this is a concurrent value optimization problem. So in structural alignment, the usual measure of overlap quality that we use is the root mean square deviation. The root mean square deviation is not by itself a good measure of structural superposition in general structural alignment, because if the number of corresponding atoms is very small, the root mean square deviation will be very low. So it is depending on the number of atoms. So usually structural alignment in general uses scores that are defined differently. For example, I define it in this way, in such a way that if the number of corresponding atoms is larger, the score is larger, and if the quality of the overlap is better, the score is larger as well. So with this kind of score, we want to determine which is the largest score, which is the largest correspondence that results in the best overlap between the structures. Finding which correspondence of the atoms is the best correspondence for a given orientation of the two structures is a problem that is actually solved, at least for sequential alignments, which is in most cases the case of protein alignment. In protein alignment, we want a sequential alignment in general, in the sense that if atom 1 corresponds to atom 3 of the other structure, we do not want that atom 2 or atom 10 corresponds to atom 1 of the first structure, because the proteins are sequential, are chains of amino acids. So in general, the alignment of two structures is a sequential alignment in terms of the sequence of the structure. So for sequential alignments, there is a solution to obtaining the best correspondence between atoms given an orientation of the structures in space, which can be obtained using dynamic programming. This is a very important classical result of 1977. So in practice, that means that for structural alignment, we know how to, given the orientation of the two structures in space, how to obtain the best correspondence between atoms that maximizes the score for that given orientation of the two structures in space. Once that we have this method to obtain which is the function, which is the concurrent function which is maximizing at that point of the domain, that means which is the concurrent function that for that relative orientation of the structures, which is the correspondence that maximizes the score, we have the correspondence, and we need now to apply a smooth optimization method to maximize that specific function for that correspondence of the movements of the proteins to maximize the score for the given correspondence. So Using dynamic programming, we find the best bijection of that maximizes the score of the structural alignment for the present position of the proteins. And now, using smooth optimization algorithms, we can maximize the concurrent function for that correspondence that consists in moving one of the structures in order to obtain the best overlap of the structures for the correspondence obtained using dynamic programming. The iterative procedure performed in this way allows us to apply both global optimization method here and the local and smooth and well-behaved local optimization method in this point. And we can define the first actually convergent algorithms that we have guarantee of convergence for algorithms for structural optimization. I won't enter into details, but the thing is that, okay, these methods are nice and practical, and they are fast, work well, and we have a server, and the methods are already published, and there is a server available, and so on. So this is the general structural alignment problem thought as a concurrent value optimization problem. Now, there is an easy problem in structural alignment that is very useful for us molecular dynamic simulators. The easy problem is the application of structural alignment within the context of molecular dynamics. In this case, we are aligning two proteins which are the same, but in different orientations or conformations along the simulation. So it's quite easy to obtain the assignment of the atoms of one structure to the atoms of the other structure, because since the atoms are the same, we do not want any assignment of atoms for which atom 1 does not correspond to atom 1 of the other structure. Only the assignments for which the atoms are really coincident within the structures are valid, since we are trying to obtain the overlap between the structures of different steps of my molecular dynamic simulations to one reference structure at the beginning of the simulation, for example. So here what we want to do is to obtain a correspondence between atoms, which is much easier because we don't have to deal with the combinatorial problem here of all assignments that are possible, and we want to minimize the root mean square deviation, which is the usual measure that we use for structural fluctuations in molecular dynamics. Typically, what we do in molecular dynamic simulations, okay, so we have many structures that correspond to the evolution in time of our protein, and we do a structural alignment, and we observe the root mean square deviation as a function of time, and we can see on our structure which are the fluctuations that are involved that are related to these fluctuations that were obtained by this structural alignment. Usually what we do is to align all atoms using a rigid body overlap strategy at each to align the structure at each point of the simulation to the initial structure of the simulation, for example. Now we are using the concurrent value optimization approach to align, which is quite easy in this case. So given a relative orientation of the two structures, that is the structure at one point of the at one time of the simulation, and the reference structure, which may be the initial structure in the simulation. For example, we can choose which are the 80% best aligned C alpha atoms. How do we do that? So we have a relative orientation between two structures in different points of the simulation. So we choose which are the 80% atoms which are closer to each other. And there is no combinatorial problem there, because we only want correspondences for which atom 1 of one structure corresponds to atom 1 of the other structure, since we are talking of the same structure at different moments of our simulation. So in order to choose which is the best correspondence of 80% of the atoms which are aligned at each point of our simulation, we just need to choose which are the 80% of the atoms which are closer to each other at that point. So we choose which are the 80% best aligned atoms, Now we align these 80% of the atoms, disconsidering the other 20%. And now this alignment will move one of the structures in order to obtain the best overlap of these 80% of the atoms. And now we have a different relative orientation of the two structures. With this new relative orientation of the two structures, we can compute again the root mean squared deviation of each atom and obtain a new set of 80% of best aligned atoms. And by applying this procedure iteratively, well, we will arrive to a moment where this iterative procedure will converge in the sense that we will obtain which is the best 80% atoms with the best relative movement of the two structures. So we are getting at the same time which is the alignment that provides to us the best subset of 80% of the atoms with the best movement, with the best overlap of these two structures for that subset of 80% of the atoms. So this is a well-defined method, which is a concurrent value optimization problem is in the same sense. So it's the same thing. So here we have multiple assignments. Now the assignment consists only in finding for each pair of structures. That means one structure from one step of the simulation relative to the reference structure is we need to identify which is the subset of atoms which are closer to each other. And so there are many possible correspondences there. So this is a concurrent value optimization problem. Instead of trying to maximize the score, here we are explicitly trying to minimize the root mean square deviation. Given the correspondence, to minimize the root mean square deviation is easy because that is a rigid body alignment problem. So we are doing the same thing as before, but now this is finding the 80% closest atoms. This is performing a rigid body alignment. This is again finding for this new orientation of the structures the 80% of the atoms that are closer to each other. And this is again performing a rigid body alignment to minimize the root mean square deviation. In practice, what we obtain, for example, this is the analysis of the mobility of this protein, the conventional analysis in which we compute the root mean square deviations as a function of time for all carbonyl C alpha atoms of the protein, for example. This is a typical result. Now we have performed the same alignment using this strategy, but the same alignment is performed now using computing which is the best superposition that obtains the best alignment for a subset of the atoms. So this is the best superposition for 70% in this case of the atoms of the protein, and this is the root mean square deviation for the superposition performed using this subset. And we can see that there is a 70% subset of the atoms that fluctuate much less than the whole structure. Of course, this must be accompanied by the fluctuations of the 30% of the atoms which are more flexible, which were excluded from my alignment strategy. So I obtain at the same time which are the fluctuations of the least mobile atoms and which are the fluctuation of the high mobility atoms which were obtained using a superposition method that is suited to find out which are the subset of least mobile atoms. So this is the overlap of the structures of the simulation using a conventional alignment strategy. This is a superposition of the structures using this strategy. So we can see here that we can clearly recognize that there is a subset of the structure which is much more preserved, and the movements of the mobile parts of the structures are highlighted in this sense because because the alignment was performed in such a way to obtain the best alignment for this subset of the atoms, leaving this part without alignment. So this can be very useful for the interpretation of molecular dynamics simulation. Okay, we have developed a software for doing this in molecular dynamics simulation, which we call MD Logo Fit, and this strategy applied in molecular dynamics simulations is published now at PLOS ONE. So you can get the software there. Now a second problem that we have been working on is the same thing, applying concurrent value optimization problems for the study of linear interaction energy models for estimating free energies. This is the problem. Actually, we wanted to know how mutations affect the stability of proteins. Generally, what we want to do is to obtain which is the free energy associated with the denaturation of a protein with a given residue in its structure. And for example, we have a mutation which changes this residue, and we have the same process of denaturation in the presence of this residue which is now changed. So the difference in free energy of denaturation of the protein with one or other residue will give us the stability or destabilization provided by that mutation to the structure. What we do in practice is we never do simulations. We generally don't do simulations of protein denaturation, but we can do simulations in which we can compute the free energy of mutating the residue in the native structure using free energy techniques, free energy perturbation in particular, and we can do models of the free energy of perturbation or free energy of mutation of the residue in unfolded models of the protein. And we can complete this thermodynamic cycle by computing which is the changing free energy of mutating this residue in the unfolded protein relative to the changing free energy in mutating the residue in the folded protein, and then we can obtain the relative stability of the protein with and without the mutation in different states. Free energy calculations are very hard. Are hard to converge, particularly for large proteins and so on. So we wanted to do an approximate strategy. So instead of doing free energy calculations, we are using an approximate model in which, for example, we are going to compute simply, instead of computing free energy, we are computing potential energy parameters alone, electrostatic and van der Waals parameters for this residue in the folded protein, for this residue in the folded protein, for this residue in the unfolded structure, and for this residue in the unfolded structure. Using only these potential energy parameters, we are going to try to fit a linear or nonlinear model to predict the free energies only from potential energy parameters, which can work or may not work, we don't know. So we are going to ask if this works. We are trying to do this in the high throughput strategy. So we are trying to study all possible mutations that this protein may undergo. In order, we are thinking the problem of designing mutations to increase the stability of a protein. So if we have, for example, a 300 residue protein, we have to perform one simulation of the native protein to obtain the potential energies of this state. We have to perform 6,000 simulations of mutant structures for simulating all the possible mutations that each residue of the protein can undergo. And we have to perform 12,000 simulations of small peptides which are representative of unfolded states of the protein for one or other residue in that sequence. So in the high throughput sense, we need to perform something like 20,000 simulations, which will be very short, and we will use only these very short simulations to compute electrostatic and van der Waals interactions of each of the residues in order to try to fit a linear model to experimental data and obtain a model that will then predict free energies using only these simplified simulations. So if we try to do that, the results are bad. So in the sense that we have tried to fit this linear model trying to predict free energies, experimental free energies, we have fitted experimental free energies to estimated free energies and obtained almost no correlation, and the standard deviation of 5 kK per mole. That means that we are not being able to predict the free energies of mutations. So what we have observed that the model fails miserably for many mutations. In particular, we see that there are many mutations here that for which the model is very, very, very bad. The first impression is that a simple potential energy approach will be not enough to predict the mutation of free energies. However, we'll be thinking of this problem in terms of concurrent value optimization. So instead of rotating and doing translations and rotation of structures and finding correspondence between atoms, we are going to fit a model. And this model will be a predicted value which will be a constant times the van der Waals, the electrostatic interactions, but plus a constant times the van der Waals interactions. So we are going to adjust the parameters A and B in order to better fit the experimental data. However, we are not going to do this for all experimental data that we have. We are going to, for an initial guess of these two parameters, we are going to choose the 80% of the data that is best fitted by our model. Then we are going to fit again our model, disconsidering the 20% of the data which is bad, which is worst. Then we are going to compute for this new model fitting, we are going to recompute which is the subset of the data which is best fitted by the model, and then recompute and again choose the 80% of the 80% best data, fit again, disconsidering the other 20% and so on. So we are doing the same kind of thing we have done for protein for structural alignment in another context. So this is a convergent value optimization problem in the same sense, and the results are that if we fit 100% of the data, we get that almost no correlation. And if we choose to fit 80% of the data, now the data is correlated with the experimental data, and we have eliminated, these are the void balls here. This data was not considered automatically by the linear fitting procedure, by the convergent value optimization fitting procedure. So this data was eliminated from the convergent value optimization procedure, and the data that remains being fitted by the data is now much better correlated with the experimental data. And now we go to 60% and it improves a little bit. Now we have, if we consider it that 100% of the data, we had almost 5% kilo-K per mole error in our estimates of the free energies of mutations. However, eliminating 20% of the data, we go down to less than 1 kilo-K per mole in the estimates of the free energies. So we can say that the model is not, our model is not really bad. However, it's very bad for a small fraction of the data. If we eliminate that fraction of the data from our estimates, we can predict with a 8% chance, we can predict a mutation of free energy with less than 1 kilo-K per mole accuracy. So this can be used to do protein engineering, for example. And you can try. You miss 20% of your guesses. You'll be probably totally wrong. However, this is much better than trying to guess without any clue which are the mutations that will improve the stability of the protein. Finally, the third problem that we are dealing with, which also can be thought in terms of concurrent value optimization problems, is the structure determination using partially wrong or ambiguous distance restraint data. What that means? We have experimental techniques that provide us information about distance between atoms in our proteins. For example, nuclear magnetic resonance experiments or chemical cross-linking experiments are methods that, in one way or the other, provide us distance between atoms of our structure, which can be used to, in principle, obtain which is the three-dimensional model of that structure. However, with both methods, particularly with chemical cross-linking, but also with nuclear magnetic resonance, The experimental data is usually very incomplete and very inaccurate. In particular, there are in both cases many distance restraints that might be wrong, or distance restraints that are correct, but that we don't know exactly within each atoms of the structure this distance must apply. Because the experimental data recognizes that there are two atoms of some chemical nature that are distant to each other at about 5 angstroms. However, there are many atoms in the same structure, particularly if the structures go larger, that are very similar from the chemical point of view. So you can recognize that there is a pair of atoms that are close to each other for a given distance, but it's very hard to know which is that pair of atoms in the structure, because there are many possible assignments for that distance in your experimental data. So we have distance between atoms of the same chemical nature, but not distance between specific atoms. So here we have also an assignment problem, which are the distance restraints that correspond to each atoms in the structures. So there is an assignment problem associated with interpreting the experimental data. So here is the experiment. From the experiment, the experiment implies different distance matrices, which overlap in some parts and are not overlapping in other parts. So different distance matrices may be obtained from the same experimental data. So for each of these distance matrices, there is a problem that consists in obtaining the structure, which is what? Is minimizing the energy of the structure subject to these penalties obtained, these constraint penalties obtained, which are defined by the distance data of the problem, but defined by the distance matrix of that problem. However, since our different distance matrix, we need to at the same time minimize the energy and find out which is the distance matrix that actually applies to our protein structure. So there is an assignment problem associated with a minimization problem of the energy of the structure. So here is the same thing. We have to obtain the assignment. There are, for each given set of constraints obtained from the experimental data, there is a function which is the energy satisfying, which is the energy as a function of the conformations of the structure that's satisfying that set of constraints. There is a different function for the same energy satisfying another set of constraints. So we have to obtain the minimum energy that we have to obtain at the same time the minimum energy and the set of constraints that have to be satisfied at each point of the domain. So this is another, again, a kind of problem that can be interpreted as a concurrent value optimization problem. Now, this smooth optimization step is to minimize the energy subject to a set of constraints. So this is a smooth optimization method being applied to the energy of the structure. And here we have given a structure in our process of structure modeling, structure optimization. You have to obtain which is the set of constraints which is best satisfied for this structure. So this defines again an iterative procedure for obtaining the set of constraints and the energy of the best structure at the same time. With this approach, this is an ongoing work. We have now obtained the first results, but I could not put them in this slide yet. We have an automatic recognition of the subset of structures which can be satisfied by the automatic recognition of the subset of constraints that can be satisfied by each structure, and we have defined a practical algorithm that can at the same time recognize the structure and the constraints that have to be assigned for that experimental data. The problem here is that the number of local minimizers is huge, so we have to we have to apply global optimization strategies on top of this optimization method. And also we might want many of those local minimizers because those many local minimizers may represent the possible fluctuations of the structure in some cases. So the message, what's that? Okay, the same. So the same thing that I already mentioned. The general message is that if one can identify that a given optimization problem that I have can be interpreted as a lower as a concurrent value optimization problem, there are ways to, if you can fulfill those two steps, which mean recognize which is the function, concurrent function, which is defining my objective function at each point of the domain. If I can do that step, I can define a practical algorithm that combines this step with a smooth optimization function, smooth optimization method in order to maximize problems. And many problems can be thought in that way as the examples I have present here. So this is the end of my presentation. Like the most software that we are developing using these strategies are available at this site. And of course, I must thank the CEPID, and repeat it here, the CEPID and the financing. We are using a lot of computational power obtained from this project, and I thank you for the invitation again, and thank you.
Thank you very much, Leandro. Any questions?
Yeah, Jim?
So when you're doing the structural optimization, I was curious about the choice of 80%, 20% in this.
Yeah.
How sensitive are the results? I mean, if you take 6 at some point.
Yeah, of course. The ideal case is that we do that automatically as well, but you can change that threshold as you want. The ideal case would be that your model fits very badly for 69% of the data, and then when you eliminate that, the next 1%, the model is very good. That would be the ideal case. So you would see a fitting that would be very bad, very bad, very bad, and then a jump for a very good fitting of the rest of the data. So this is the ideal recognition of which is the subset of atoms or subset of data that's being fitted by the model you are proposing. Of course, in practice, you can get different levels of smoothness of this jump, but you can check that if that occurs. You know, in particular, if the situation is very bad, there is no jump at all. That means that your model, you are just increasing the noise of the data at every data that you are adding in the model.
Is this this method of talking about the structure fitting? Is this a global optimization? I mean, does it matter where you start, for example?
Yeah, it does matter. It does matter. Yeah. You can, for example, of course, I have drawn examples in which everything goes well, but we can, for example, if we started from this point and we are trying to minimize the root mean square deviation, the best structure would, the best correspondence would get us to this point, and then the rigid body movements will lead us to this local minimizer. And in that case, the algorithm will stop because it recognizes that you are already in a minimizer. So if you want actually the global optimization procedure, you have to couple this method with a global optimization strategy. But this is well defined for the local optimization point of view.
Right, so again, think about it practically. I mean, it looks really interesting from a practical point of view, and I'm very interested in it. But if you apply it to a molecular dynamics trajectory, well, I mean, you just kind of assume that if you start at the beginning and work your way to the end, you'll be okay, or do you experiment practically?
You can actually experiment. Our implementation of for the superimposition of structures in the molecular dynamics simulation, our implementation tries 1,000 different initial orientation of the structures. What that defines, for each given orientation, you have a different assignment of the atoms to start with. So for that given assignment, that defines a movement, and that defines a new assignment, another movement until convergence. So given the first assignment, you can go to one or other local minimizer. So the implementation we have tries 1,000 different initial assignments, but this is very fast. It takes nothing. The algorithm is very fast in this case. That might be a problem for a different problem, but in the case of structural alignment, this is not really a problem because the iterative procedure is very fast, so you can do 1,000 tries in less than a second.
More questions?
I have one more. On this mutation free energy stabilization example is really nice. I was wondering, so you made the comment that you find this set of mutations for which it works, and then you have a set when it doesn't work.
Yeah.
How do we learn from the failures? Because if you want to take a concept like this and do protein engineering, of course, the failures are, in some sense, as important as the success, right?
Yeah, exactly. Yeah. Actually, we could look, for example, in this case, this is the reason why I didn't publish these results yet. There is, in this case, when we look to this, the structures, the mutations which were eliminated from the fitting, mostly are mutations which involve very strong electrostatic interactions. Okay. So we can learn from that. So my model, the way I'm trying to fit my model is being very bad for very strong electrostatic interactions. So I could avoid that kind of thing. But that changes depending on how I define the model I'm fitting.
Yeah.
I am simply defining a very simple crude model here. I could change the variables here in order to fit better some other subset of the data. That depends on the model I'm trying to fit to the experimental data. So yes, this is an important part of in understanding how this goes in terms of the molecular nature is an important part of understanding this result.
At one point, perhaps one way of improving this would be to consider some explicit role of water for the part that is denatured, for instance.
We do that. Actually,
not just in terms of the interactions, but maybe binding. Entropic contributions, for instance, when you have strongly.
Yeah, we are computing the average potential interaction energy of each residue with the whole environment. So in some way, there is an average there for a very short simulation time. We could maybe introduce some entropic effect in the sense we're talking using the implicit solving. That would be more explicitly. But what we're doing now is simply performing a very short simulation in which we are computing the potential energy parameter from that simulation. But we could add other kind of parameters in that would define a different model to do.
May I ask one question? If nobody has one question, I have one question. I'm missing an important point, I guess, which did not make the connections here. In the last applications, your concurrent functions, they are of a different nature. You have energy in one side and you have RMS data on the other side. So
no, here, this last one. No, we are trying to minimize. Yeah, we are trying to minimize the energy, and at the same time know if that the structure we are obtaining is fulfilling a subset of the constraints that we're obtaining from the experimental data. There is no structural alignment there anymore. What we do is to add the constraint penalty to the objective function, an energy term that is defined by the constraints that we are trying to fulfill. And which are the constraints that are being added to this energy are chosen, the subset is chosen using the convergent, the concurrent function.
Okay, so the images, not the domains, the images of the concurrent functions, they have to belong to the same class of quantities.
Yes.
Any other further questions? Or
just a quick follow-up on the NMR one. I mean, classically, most NMR spectroscopists, they just say, well, I'll get a family of models, each of which within it satisfies a certain percentage of the constraints. So can you apply that kind of thinking to this? Yeah,
exactly. This is one of the problems we are trying to deal with. However, in the specific context of NMR, this is somewhat solved. They have strategies to deal with that kind of ambiguity of of the distance restraints. But yes, this is an alternative strategy for the same problem. So we are dealing both with the NMR, with trying to introduce a new strategy for the assignment of NMR restraints, and at the same time with this other kind of experiments, which is the chemical cross-linking, which is a different nature of experiment. We are dealing with both things.
If any have any other questions, let's thank Leandro again for wonderful talk. And next.